A thin curve floats on a dark screen, quiet as a horizon at night. One smooth arc of light versus wavelength. Then in one narrow place, a small bend. A dip that looks like a fingerprint. Someone has circled it. Someone has dared to label it. Methane. This is the exoplanet WASP-39b. Not as a world you could stand on, but as a measurement you can barely hold. An atmosphere inferred from a shadow. A planet we never see directly, only the way starlight changes when it passes through a rim of gas. That is the premise of spectroscopy. In transit, not a picture, but a subtraction. And in that subtraction, a feature appeared. A line. Something that for a moment looked like it belonged to a molecule. But the title of this story is not about a discovery, it's about a refusal. The NIRISS line on WASP-39b wouldn't hold. It refused to fit the way we wanted it to fit. It pushed back against certainty. And in the quiet language of science, wouldn't hold is not a shrug, it's a warning. This might be signal, or it might be a confounder wearing signal's clothes. So what does it mean physically and statistically for a line not to hold? Start with the most human temptation. The mind loves patterns. We have evolved to see faces in shadow, meaning in noise. In exoplanet atmosphere, work that instinct has a scientific cousin. We see a small structure in a spectrum, and we want it to be a nameable gas. A story, a chemistry, a clue that the atmosphere has a particular ingredient. But a line in this context is not a line you can touch. It's a subtle change in how much light is missing at a particular wavelength. A tiny difference between starlight before the planet passes in front and starlight during that passage. The measurement is the planet's effective size as a function of color, how thick the atmosphere seems when seen in different parts of the spectrum. And in that small difference, small enough that every step matters, something can go wrong without anyone being careless. The first meaning of wouldn't hold is simple: repeat the analysis, and the feature weakens, shifts, or loses its uniqueness. You push on the inference, and it changes shape. You try a reasonable alternative calibration choice, and the line isn't as persuasive. You test a different modeling assumption, and what looked like methane starts to look like something else, or starts to look like nothing at all. That's the hard truth. At the edge of certainty, the line exists in a narrow space between what the data contain and what our pipeline extracts. Between photon and conclusion, there's a chain of decisions. In the cleanest version of the story, a molecule leaves a structured imprint and we recognize it. But nature doesn't owe us clean stories, especially not in an exoplanet atmosphere. Because WASP-39b's atmosphere is not only gases. It can be particles, clouds, hazes, aerosols layers that scatter and swallow light in ways that blur molecular fingerprints. Clouds and hazes can mute features, flatten contrasts, and make a spectrum look featureless in places where chemically there may be plenty going on. They can also make one region look deceptively structured if the baseline is shaped just so. And then there is the machine itself, the part we almost never want to talk about when the curve is pretty. Instrument systematics. The subtle quirks of detectors. The tiny shifts and drifts that can look at first glance like physics. In a spectrum, this delicate wavelength calibration and detector behavior aren't background, they're potential authors of false detail. A line can be born from a correction, or erased by one. So the honest question isn't, is methane there? Not yet. The honest question is the feature robust to the ways we know this kind of data can be fooled? Because an exoplanet atmosphere can lie to us in at least 3 voices. The first voice is the planet itself through clouds and hazes. It says even if the gas is there, I can hide it. Or I can make you think I've hidden it. The second voice is the star. Stellar contamination patches of spots or bright regions on the star's surface can change the apparent depth of the transit in a way that depends on wavelength. It can mimic an atmospheric feature or mask one because what we call planet spectrum is always planet plus star mixed together. And the third voice is the instrument systematics that can produce small coherent structures, not random noise, coherent behavior. The kind that looks like a real line until you demand it survive independent checks. This is why wouldn't hold matters. It's a credibility phrase. It's the story's spine. It tells us we are not watching an announcement. We are watching a trial. And in a trial, evidence has to be cross-examined. Here is an evidence moment you can feel without a single number. Take that circled dip and watch what happens when you change the lens you're looking through figuratively, not physically. A different reduction, a different way of correcting time trends, a different set of reasonable assumptions in the retrieval. If the methane label is truly anchored in the photons, the feature should persist. It should keep the same identity. If it doesn't, if it slips away, then the feature may be telling us less about methane and more about vulnerability. And vulnerability is not failure, it's information. We should be clear about what we know and what we are tempted to infer. We know that transit spectroscopy can reveal wavelength-dependent signatures consistent with molecules and aerosols in an exoplanet atmosphere. We know that clouds and hazes can reduce the contrast of spectral features, sometimes flattening spectra, sometimes reshaping them. When a feature changes under plausible analysis, choices when it wouldn't hold, it suggests low signal-to-noise degeneracy with clouds or sensitivity to systematics. And then there is the edge case, the possibility that keeps humility alive. A line might be real but variable, changing with atmospheric dynamics, so a single observation could catch a temporary state. The problem is variability can look exactly like weakness when you don't yet have enough repeated looks. So we don't pretend the mystery is solved in the first act. We sharpen it. WASP-39b is our named target, but it's also our stand-in for every future claim about an exoplanet atmosphere, especially any future talk of signs of life. Because if we can be fooled by clouds versus methane on a hot planet, we can certainly be fooled when the stakes are higher and the signals are smaller. False positives don't announce themselves. They arrive wearing confidence, and the title keeps its promise by refusing comfort the NIRISS line on WASP-39b wouldn't hold. The real reason is not one dramatic twist. It's the slow weight of alternative explanations. So now we do what careful science always does next. We take the two rival stories and make them stand side by side in the same light. Is it methane, an atmospheric ingredient, leaving a chemical signature? Or is it a mask, clouds and hazes, shaping what the spectrum is allowed to reveal? We move forward not to declare a winner too soon, but to understand what each story would look like if it were true, and how each could fool us if it were not. The spectrum returns, but now it's split down the middle, two quiet stories told in the same faint starlight. On one side, a curve with structure the kind our brains want to call a molecule. On the other, a curve softened and subdued as if the whole atmosphere has decided to hold its secrets close. WASP-39b doesn't give us a photograph. It gives us a problem in spectroscopy. And the problem is this: the same exoplanet atmosphere can be explained in more than one way, especially when the signal is subtle and the confounders are strong. Detection versus interpretation. Signal versus artifact. That's the tension we live in. So we bring the two suspects into the light methane and cloud. Methane is tempting because it's a name, a chemical with a recognizable pattern. In the simplest intuition, methane means there is carbon chemistry happening. There is a set of bonds that absorb light in specific places. In a transmission spectrum, methane would appear as a structured absorption, feature one part of the curve, dipping more than its neighbors. Clouds, by contrast, are not a single chemical. They're a condition. A layer of particles condensates aerosols, hazes, that changes the rules of visibility. Clouds don't have to match a neat fingerprint. They can mute fingerprints across wide swaths of wavelength. They can impose smooth slopes, flatten contrast, and shrink the difference between this gas is present and this gas is hidden. Now, the key question in a hot exoplanet like WASP-39b, what would methane look like in NIRISS? And how could clouds imitate it? We answer it without pretending we have more than the outline allows. First, methane. Methane abundance depends on temperature, chemistry, and mixing. In some atmospheres, it can be produced, destroyed, transported, kept out of equilibrium. But in hot conditions, methane can be less stable than many people expect from Earth intuition. That matters because it changes what counts as plausible when we interpret a spectrum. A methane feature might be real, or it might require special conditions that should make us cautious. Second, clouds and hazes. In transmission spectroscopy, what we see is the altitude where the atmosphere becomes opaque at each wavelength. If clouds sit high, they can raise that opacity floor. They can block light from reaching deeper layers where molecular signatures would otherwise be stronger. The result can be a spectrum that looks smoother, less distinctive, sometimes almost flat. Here's the cruel part. Clouds can do more than hide. They can also mislead. If clouds shape the baseline, and if the data are tight enough to show a small deviation from that baseline, our models may interpret that deviation as a gas. Not because anyone is lying, because the math is trying to explain a curve with the ingredients it has been offered. This is cloud/haze degeneracy. The same observed spectrum can be matched by different combinations of aerosols and gas abundances. That's why the title's conflict clouds versus methane isn't just two options. It's a warning about how inference works when you're near the edge. The title thread pulls us back again. The NIRISS line on WASP-39b wouldn't hold. If the methane-like feature refuses to fit consistently, we don't get to treat methane as a settled detection. We have to treat it as a hypothesis, under pressure, competing with the quieter, more common explanation that a veil of particles is shaping what starlight can reveal. So what does a fair trial look like? It starts by acknowledging that a single narrow feature is a fragile foundation. If methane is truly responsible, the explanation should not feel like a one-off miracle. It should cohere with the broader spectrum and with reasonable atmospheric physics. In this outline, we keep it honest. Methane may be possible, but the confidence rises only with consistency across checks, especially across wavelength regions. And if clouds are responsible, the story often has a certain gravity. Clouds are common and their effects are broad. They don't require the data to align in a fine, delicate way at one spot. They can simply suppress contrast. In a world where we are trying to read an exoplanet atmosphere from a faint rim of light, that kind of broad explanation often survives longer. This is the central evidence moment of this section. Put two models on the same data, and both can look convincing in one region. A methane world curve can track the feature. A cloudy world curve can also track it, especially if the feature is small and the baseline is uncertain. The eye sees a match either way. The danger is thinking that a match is the same thing as a unique identification. And that's where retrieval enters, not as a magic answer, but as a disciplined way of asking, what combinations of atmosphere parameters can explain the spectrum and how sensitive is the conclusion to what we assumed going in retrieval, is where model assumptions become destiny if you're not careful. We name the confounder explicitly because it's the point retrieval priors and model assumptions. 1D versus 3D atmospheres, equilibrium versus disequilibrium chemistry, temperature profiles that change what gases should be present. Each choice can tilt the balance between methane and clouds. A retrieval can prefer methane not because methane is truly demanded by the photons, but because the prior space makes clouds harder to express or vice versa. So we adopt the only posture that fits a serious search for signs of life. We treat methane here as a lesson, not a trophy. Not because methane is a biosignature on WASP-39b. It isn't our life story, but because the logic is the same. Any future biosignature claim will face the same trial chemistry that looks meaningful versus the false positives that mimic it. If we can't separate methane from clouds with confidence on an easier target, we should be humble about harder ones. And still, we leave the door open, not to hype, but to possibility under constraint. Disequilibrium chemistry could create unexpected methane levels, but only if the spectrum supports it in a way that isn't easily replicated by clouds and isn't a byproduct of assumptions. So by the end of this section, the viewer should feel the shape of the dilemma. Methane is a specific story. Clouds are a masking condition. The same starlight can be read as either, unless we understand exactly how the measurement is made and exactly where it can be fooled. Which brings us to the next step, the one we can't avoid if we want to be honest. We have to go down into the machinery of inference, into the art of subtracting starlight, because that's where a line can appear, and where it can fail to hold. A stream of photons hits a detector and becomes a row of numbers. Cold, impersonal, a time series. And somewhere inside that arithmetic, buried under the star's brightness and the telescope's own habits, there may be the faintest imprint of an exoplanet atmosphere. Not a picture, not even a silhouette really. Just a slightly deeper dimming at some wavelengths than at others as WASP-39b transits and a thin ring of starlight skims through its air. This is the moment where wonder has to become procedure. Because the title's promise lives here, the NIRISS line on WASP-39b wouldn't hold. A line doesn't fail in the sky first. It fails in the chain between raw measurement and interpretation, where we turn photons into a transmission spectrum and then into a claim. So how do we actually do it? What steps turn a transit time series into a transmission spectrum, and where can a line be born or break? We start with the most basic idea, the one people can hold in their hands. During a transit, the planet blocks a small fraction of the star's light. That part is simple, but at different colors of light, the planet can block slightly more or slightly less, because its atmosphere is more opaque in some wavelength than others. That difference, tiny wavelength by wavelength, is the entire game of transmission spectroscopy. And it's a subtraction game. You collect starlight before the transit. You collect starlight during the transit. You compare them across wavelengths. What remains after careful correction is the planet's effective radius as a function of wavelength, a curve that encodes the atmosphere's absorption and scattering. Now the first evidence moment is this: the curve is not read off the detector. It is constructed. It exists only after you correct the data for everything that is not the planet. That correction has layers. First, extraction, turning the detector's recorded signal into flux as a function of time and wavelength. Then, wavelength mapping, knowing which detector pixels correspond to which wavelengths. Then, light curve, building measuring how the star's brightness changes through the transit in each wavelength channel. Then trend removal, removing slow changes unrelated to the transit. Then combining turning many channels into a spectrum. Each step is a potential doorway for instrument systematics, subtle detector behavior, thermal stability, issues, calibration, drift wavelength, calibration offsets. These aren't exotic failures. They're normal engineering realities that must be modeled and corrected. And because the atmospheric signal is small, the corrections can be the same size as the thing we're trying to detect. This is why the phrase "wouldn't hold" has teeth. A line can appear when one reasonable set of corrections is applied and weaken when another equally reasonable set is used. Not because anyone is cheating, but because the line lives close to the edge of the instrument's own personality. So in a careful analysis, you do not treat one pipeline as scripture. You test. You process the same data through alternative reductions. You check whether the feature remains. You ask, does the line keep its identity, or is it sensitive to the choices we made? A robust atmospheric feature should survive that pressure. This is not a philosophical standard. It's practical survival. And there's another quiet truth the audience should hear. Plainly, the star is not a blank light bulb. Even if JWST and NIRISS were perfect, the star itself can imprint wavelength-dependent effects on the transit depth. The star has spots and bright regions in homogeneities on its surface. If the planet crosses different parts of the stellar disk, or if unocculted spots and faculae change the star's effective color, the transit can look deeper or shallower at certain wavelengths for reasons that have nothing to do with the exoplanet atmosphere. This is stellar contamination, and it matters because it can masquerade as a molecular feature or erase one. Here is the second evidence moment. If you don't explicitly test for stellar contamination, you can misattribute the star's chromatic texture to the planet's chemistry. A dip that looks like methane could be the star's surface pattern filtered through the transit geometry. The measurement is always planet plus star until proven otherwise. So a responsible how we know chain has to include diagnostics. Does the inferred spectrum correlate with indicators of stellar activity? Does the feature appear in a way that suggests a stellar origin? Smooth, broad chromatic changes that track what spots and faculae would do? Or does it behave like a planetary absorption feature that fits into a coherent atmospheric model? This isn't about winning an argument. It's about refusing a false positive. And then there's the part of the chain where the spectrum becomes a story retrieval. Once you have a transmission spectrum, you ask what combinations of atmospheric parameters could have produced it. Gas abundances, temperature structure, cloud opacity, haze scattering. Retrieval is not a single answer machine. It is a disciplined mapping from data to a range of explanations, given a model and given assumptions. And those assumptions are where fragile lines often reveal themselves. You change a prior, you change a cloud model, you change an assumption about chemical equilibrium, and a methane interpretation can tighten or dissolve. That sensitivity is not merely annoying. It is information about how much the data actually constrain the claim. This is where the title's credibility framing comes back explicitly, and without drama, the NIRISS line on WASP-39b wouldn't hold. The real reason may be that the data do not uniquely demand methane once we account for clouds, systematics, and stellar contamination. Or that the feature is real, but too close to the noise and model degeneracies to carry the weight of a detection yet. Now, we do not leap beyond what we have. We do not invent a definitive gotcha. We stay inside the logic. Transmission spectroscopy compares in-transit and out-of-transit starlight across wavelengths to infer an exoplanet atmosphere's effective radius as a function of wavelength. Calibration includes detector behavior corrections, wavelength mapping, and trend removal across time, each a potential source of systematic structure. If a feature changes with plausible calibration choices, it suggests sensitivity to instrument systematics or insufficient baseline to disentangle signal from drift. And here is the cautious door we leave open. Cross-instrument confirmation. Overlapping wavelength checks and independent pipelines can transform a fragile line into a durable detection if it persists in the same physical form. The visual metaphor is almost too perfect to convey about. Photons go in, a spectrum comes out. But between them at each station, you can either remove a contaminant or accidentally add one. The art is not in believing the final curve. The art is in trying to break it. So what do careful teams do to increase confidence? They use redundancy. Alternative pipelines. They look for stability across time, across wavelength channels, across methodological choices. They perform injection recovery style reasoning, asking in essence whether a known feature would survive the pipeline and whether a spurious feature could be created by the corrections. They compare results across independent reductions. They check whether the line is a local oddity or part of a consistent pattern across the spectrum. And every time they do that, they are reenacting the deeper ethic of exoplanet atmosphere. Work distrust your first beautiful explanation, because the cost of being fooled is not embarrassment. The cost is building a tower of inference on a false positive, especially when in other contexts we will be looking for biosignatures or even speculative techno-signatures tied to atmospheric channels. The discipline begins here with methane and clouds long before anyone is tempted to say the word life. So we return to the case of WASP-39b with a steadier definition of what wouldn't hold truly means. It means the line has been asked to survive contact with the real world, the star's imperfections, the instrument's personality, and the model's assumptions. And it did not yet earn the right to be called a single clean molecule, which is not an ending, it's the threshold. Because the next question is not who is right. The next question is, what is the most intellectually honest conclusion we can live with today? Clouds, first methane on probation, and why that restraint is not a defeat, but the very shape of progress. Now we confront the uncomfortable part. The line doesn't just need a story. It needs to survive every attempt to kill it. The spectrum is still there, hovering like a quiet shoreline. The same faint curve, the same circled region. But the circle feels different now, less like a treasure map, more like a warning label. Because when a feature refuses to stay put, when it wouldn't hold under scrutiny, you don't get to keep speaking in absolutes. You don't get to treat a convenient explanation as a conclusion. You make a change of perspective. You stop asking, what do I want this to mean? And you start asking, what can I defend? This is where we land the best current conclusion without theatrics. On WASP-39b, the NIRISS line wouldn't hold in the way a confident molecular detection has to hold. The title's promise is not a twist, it's a discipline. The real reason is that the evidence as framed by the outline points toward a more stable reading clouds and hazes. First methane on probation. Not ruled out, not crowned, constrained. So what is the most intellectually honest read of WASP-39b's NIRISS feature right now? We begin with what we can say cleanly. Clouds and hazes commonly mute spectral features in exoplanet atmospheres. They change how deeply we can see into the atmosphere during a transit. They raise a kind of opacity floor. The planet may still have molecules below, but the spectrum becomes less willing to reveal them. And that matters because it makes clouds a powerful default confounder. Not because clouds are always the answer, because clouds are often the easiest way for the atmosphere to hide complexity. A broad physical effect that can dominate the shape of the transmission spectrum. Now we return to the tension that defines this episode's signal versus confounder. If a methane claim rests on one narrow low-margin feature, and that feature wouldn't hold across checks, then the cautious conclusion leans away from calling it a detection. It leans toward interpreting the region as something that may be shaped by clouds, by subtle systematics, or by model sensitivity. This is the evidence moment. The methane-like label does not survive as a unique explanation. The feature does not demand methane in a way that overwhelms alternatives. In a courtroom, it's evidence that can be challenged. Not nothing, but not enough to convict. So we shift how we speak. Instead of methane detected, we speak in bounds, in conditions, in what the data can support without collapsing under reasonable skepticism. Methane becomes something we can limit an upper range, a conditional range depending on retrieval outcomes. The story becomes less cinematic in one sense, but more honest. And the honesty is the point. This isn't retreat, it's precision. Because the pursuit of signs of life in exoplanet atmospheres will demand this exact restraint. Biosignature claims will live and die on whether we can distinguish chemistry from confounder. False positives from real planetary physics. A story that fits from a story that is forced. So we place the verdict scale on the table. On one side, cloud opacity. On the other, methane detection. The scale tips toward clouds, not because methane is impossible, but because clouds are consistent with the broader logic of transmission spectra and with the fragility implied by wouldn't hold. And we do something else the audience can feel. We stop romanticizing a single line. In a mature reading of exoplanet spectroscopy, one feature is rarely a standalone truth. It must make sense alongside other parts of the spectrum. It must cohere with plausible atmospheric physics. It must persist. If it doesn't, we keep it in a different category, a clue, not a conclusion. Now we name a specific trap that remains even after we decide to be cautious, line misidentification. Even if the spectrum has a real feature, assigning it to the right molecule depends on the completeness and accuracy of line lists, our catalogs of how molecules absorb at different wavelengths. If line lists are incomplete, or if multiple absorbers overlap, a subtle feature can be attributed incorrectly. And when the signal is small, that attribution can swing with assumptions. So we say, it plainly line misidentification, and incomplete line lists are a confounder here. They can bias molecular attribution, especially when the feature is subtle and competing explanations remain viable. That's the limitation we carry into our conclusion. And still we allow for the future without pretending it's already here. Methane could be rehabilitated by multi-wavelength consistency correlated features appearing where methane should also imprint in a way clouds cannot easily mimic, and in a way systematics are unlikely to reproduce. Not by one persuasive dip, but by a pattern that repeats with physical logic. That is what would make the line hold. So the change of perspective is not simply clouds win. It's a shift from binary thinking to disciplined uncertainty. Clouds/hazes can flatten and reshape transmission spectra. If the feature refuses to fit consistently, if it wouldn't hold, then a cloud-forward interpretation is the stable place to stand, and methane is treated as conditional. And that conditional posture is the best current conclusion. Quiet, slightly ominous if you think about what it implies, even with exquisite instruments, even on a well-studied exoplanet, the atmosphere can keep its secrets behind a veil. And our models, our assumptions can tempt us into naming what isn't uniquely demanded. Which brings us to the final turn. Because this isn't just about one hot planet. It's about the rules of belief we carry forward into the search for life's gases and even the most careful, speculative techno-signatures tied to atmospheric channels. It's about learning again and again that the universe rarely speaks in single lines. We widen the lens now not into cosmology, not into fantasy, into a cosmic checkpoint, into limits, into what atmospheres can do to our hopes and what future data must measure to resolve the named unknown that still hangs over this case. We go forward with one measurable question still on the table: cloud opacity versus methane abundance. The fog rolls in across the spectrum first, not as weather, but as physics. A widening smoothness, a flattening that spreads quietly like a curtain drawn across a stage. The circled notch that once looked like a fingerprint becomes harder to defend as a singular truth. It doesn't disappear in a dramatic way. It simply stops behaving like a reliable witness. And that is the cosmic checkpoint, not a triumphant discovery, not a failure, an honest boundary line. Because the search for signs of life in an exoplanet atmosphere will not begin with certainty. It will begin with shapes like this, with a hint that could be chemistry, or could be a confounder, or could be the instrument's own shadow. The discipline we practice on WASP-39b is the discipline we will need when the signals are smaller and the stakes are louder. So we ask one last time, the question that matters. Now what exactly must we measure next so clouds versus methane stops being an argument and becomes a resolved physical claim? We name the uncertainty without hiding it behind abstraction. The named unknown is measurable cloud opacity versus methane abundance in WASP-39b's transmission spectrum. Not a feeling, not a vibe. A degeneracy we can quantify. A question the data can answer if we give it the right chance. And the title thread returns with its quiet warning: the NIRISS line on WASP-39b wouldn't hold. The real reason in this telling is not that the universe is teasing us. It's that weak signals in spectroscopy are easy to overinterpret unless they survive tests against false positives. Now we rotate through the confounders with the seriousness they deserve. First instrument, systematics. Thermal stability detector affects wavelength calibration, small drifts that can sculpt a feature where none exists or erase one that does. If a line is perched near the edge of detectability, the instrument can become an uninvited co-author. That is signal versus artifact in its purest form. Second, stellar contamination. The star is a surface, not a lamp spot's faculae heterogeneity. Chromatic effects that can change the transit depth by wavelength for reasons unrelated to the planet's atmosphere. Without explicit modeling, planet atmosphere and star contamination can masquerade as each other. That is planet versus star, masquerading as chemistry. Third time variability versus sampling. This is the confounder that turns a single beautiful dataset into a trap. Too few transits, a baseline that's too short, a feature that seems to appear, then fails to repeat, not because it was false necessarily, but because we sampled the system imperfectly. Sampling can turn reality into inconsistency, and inconsistency can masquerade as weakness. That's why wouldn't hold can mean more than one thing. Here is the evidence moment that follows from the outline's logic. To resolve this, we don't need rhetoric. We need redundancy. To show up with correlated features, to show up with correlated features elsewhere, not just in one fragile region. Cross-checks that make it harder for clouds to impersonate methane and harder for systematics to impersonate the planet. And that's the key. Methane doesn't get rescued by faith. It gets rescued by consistency. If methane is real, it should leave a pattern that repeats across wavelengths in a way clouds alone cannot easily fake. If clouds are the dominant actor, their signature muted contrasts, scattering behavior should cohere across wavelengths too. Broader coverage is not more data for the sake of more. It is a way of forcing nature to speak in complete sentences instead of single syllables. This is where we place the case of WASP-39b back into the larger exoplanet story, carefully without drifting. WASP-39b is not an habitable zone. It is not our candidate for life, but it is a rehearsal for the logic of biosignatures and the caution we must bring to them. If clouds versus methane can confound us here, then on temperate worlds, where the signatures may be smaller and the host stars may be more active, the false positives will be more seductive. Biosignature claim versus false positives. That tension doesn't begin when we say oxygen. It begins here when we decide whether to call methane real or conditional. And if we ever speak of techno-signatures in the same breath, we keep them grounded in observational channels and wrapped in humility. Industrial gases, unusual atmospheric constituents, nightside light, these would live in spectra, and photometry and inference chains like this. And they would be vulnerable to the same confounders, contamination, systematics, model assumptions. The lesson is not that anything is impossible. The lesson is that extraordinary interpretation requires extraordinary resistance to being fooled. So the checkpoint is not cosmic in the sense of distance. It's cosmic in the sense of method. The universe gives us thin evidence. We build meaning carefully. Then we try to break our own meaning with the best confounders we can name. That is how exoplanet atmosphere science stays honest. Atmospheric interpretation is vulnerable to stellar heterogeneity instrument systematics and cloud/haze degeneracy. Robust claims require redundancy, multiple wavelengths, repeat observations, cross-checks against star and instrument behavior. And the last beat is not despair. It's a kind of quiet awe at what this method can do, even at its limits. Because even when a line wouldn't hold, it still taught us something true. What certainty costs when we read an exoplanet atmosphere from a shadow. The closing images come softly. The highlighted methane notch on the spectrum dissolves into a broader, flatter curve fog, filling the frame not as failure, but as the atmosphere's signature asserting itself. 2. The transit silhouette again, WASP-39b, cutting across its star, its atmospheric rim faintly luminous, then dimming as the star's own chromatic texture overlays the measurement. And the lingering sentences we leave behind, without hype, without comfort. Sometimes the universe doesn't answer with silence, it answers with a signal that refuses to hold until we learn how to listen. The line didn't fail us. It taught us what certainty costs when we read an exoplanet atmosphere from a shadow. The named unknown remains measurable, resolvable, waiting for the right kind of patience. Cloud opacity versus methane abundance. And what will resolve it is not persuasion, but future data built for cross-examination. More transits, broader wavelength coverage, and explicit modeling of the star and clouds together until the spectrum stops being a suggestion and becomes a constraint.